Hello everyone, and welcome to this afternoon's session on cloud-native storage and the storage tag. So this is a maintainer session. My name's Alex Chircop. I'm a chief architect at Akamai and newly elected to the CNCF TOC, which is the Technical Oversight Committee.
Hello, my name is Xinyang. I work for VMware by Broadcom. I'm one of the co-chair of Tag Storage.
And Raffaele Spazzoli, I work for Red Hat as a consultant, so lots of customers interaction, also co-chair.
Fantastic. And we wanted to use this session to talk a little bit about the tags, but more importantly, how the tags are being restructured, because we're looking at a reboot of the tags and the CNCF projects and initiatives as part of this KubeCon, and we'll have a new structure coming out soon. We're also going to talk a little bit about why cloud-native storage is important, but then we're going to focus on some of the data and Kubernetes white paper and cloud-native disaster recovery. So what is the tag anyway? So the tags are technical advisory groups. They work with the TOC, the Technical Oversight Committee, to help with project evaluations and to provide guidance to the TOC on the subject matter expertise, as well as work on various initiatives like some of the white papers which we're going to talk about. Now, I mentioned we're about to go through a tag reboot. So we're consolidating the 8 tags to 5, and we're going to also be putting together a new structure around initiatives and sub-projects to help reinvigorate the process and also set us up for the scaling that we need to do for the next 10 years. At a very high level, we have the TOC as a top-level body. The tag groups are going to be organized around these 5 new areas that will focus on, a specific domain. We're going to have sub-projects which are going to be targeted at some long-running things, like, for example, security assessments, but also project reviews. And initiatives which will be either aligned to a tag or the TOC, that will be specific initiatives to either help projects or help the way the CNCF operates. And of course, we can't do any of this without the community that goes around it. So we'll be also defining a number of community groups that will help, come up with ideas and innovation that will, hopefully spur on a number of initiatives and projects. There's a lot more detail, and please look at the PDF on the shed for the links, and feel free to contribute and add any feedback to the GitHub issue that's ongoing. So why all of this scaling requirement? The reason is that the number of projects has dramatically grown since the tags were first conceived of in Barcelona in 2019. So, we've kind of gone from about 40 projects to 215 projects in that time frame, and now we're continuing to see huge amounts of growth. So just in the last year, another 33 projects have been added to the CNCF, and we want to make sure that the organization is now also able to deal with the huge influx of projects, but also maintaining and sustaining, the health of the projects as we go along. Okay. Going to flip to cloud-native storage, because this is the tag storage talk. So why should we talk about this? The most obvious thing is, we always think about cloud-native as stateless, but there is no such thing as a stateless architecture. At the end of the day, every application is needing to store data somewhere. And our thesis is that we want to be able to use all of the advantages of Kubernetes and the cloud-native environments to automate and have failovers and scale, etc., for all of our cloud-native workloads too. Because we want them to be declarative, we want the automation, we want the performance, we want the failover capability. And not only do we have broad ecosystem and CSI support and also COSI support now, for integrations with, block and object store, but we also have a really rich and mature environment for operators that automate complex database topologies with automated replication and failover, automating message queue delivery, and many more things. There are a number of very large graduated CNCF storage projects, including Rook, which automates Ceph environments for both block and object storage and file systems, Vitess, which is a scale-out MySQL database operator, Harbor being a container repo, etcd, of course, you're all familiar with your Kubernetes clusters, TIKV, which is a very scalable key value store, and KubeFS, which just graduated a couple of months ago, and KubeFS provides a really great shared file system, which is especially useful for machine learning workloads and AI nowadays. And of course, we have a number of incubating projects, and I would also encourage you to have a look at the links below to see the huge plethora of other incubating projects and sandbox projects which form part of the CNCF. When we talk about the projects, and we sort of mentioned slightly there the graduated and incubated projects, I just want to very briefly touch on what each of those stages refers to. So a lot of projects join the CNCF as sandbox projects, and those sandbox projects are there to help build the community, build their IP, build some of the governance, etc. And of course, it's also there to help experiment. Incubation projects have a very high bar in terms of the due diligence. And in order to get to an incubation, you have to go through not just a due diligence procedure, but we also need to speak with adopters and make sure that that the project is being used live in production. So being used successfully in production is sort of one of the biggest I guess grades that you get with incubation. And then further beyond that, graduation means we have enhancements around security and security audits, for example, which the CNCF pays for. And we also get we also focus on governance. So, for example, making sure that we have contributors and maintainers from multiple organizations to ensure the ongoing health of the project. If you're interested in, if you're a project that's looking to apply, some of the domain technical reviews, or the DTRs, provide a number of the questions that we are going through when we look through the due diligence, and kind of forms a template as to what the projects go to when moving levels. I'm going to speak very briefly about the CNCF Storage Whitepaper now. This is one of the projects or initiatives that the TAG has worked on for a number of years. In the white paper, we cover the attributes of the storage system and some of the layers of the storage system, and how you access different areas of the storage system. And bear in mind that storage in this case is not just block or file system, but it's also object storage and key value stores and databases. And we are also just about to release a version 3 of the white paper, which has some updates and also includes other areas like messaging and streaming. I'm going to just pop this up on the slide, but one of the things that we talk about is the storage attributes and the various areas that you want to look at. The main thing I'm going to emphasize here is that this is a way of trying to figure out what your application needs, and therefore how you map that to the different type of storage solutions which are available, because different applications have different requirements and one storage solution doesn't work for all. And similarly, it's also really good when you're looking at cloud-native storage systems to understand the various layers that form the storage system, because there are various layers of virtualization. And you often have, for example, say a file system that might be built on object storage and therefore shares some of those attributes with the object storage. And there are many examples of different storage systems based on multiple layers. And with that, I'll hand over to Jing, who's going to talk about a bit the data workloads in Kubernetes.
Thanks, Alex. According to the survey by Data on Kubernetes community, more and more safer workloads are moving to Kubernetes. These workloads move into Kubernetes to take advantage of Kubernetes self-healing abilities, agile deployment, scalability, and portability. The DOK report shows the evolution of data workload types over the years between 2021 and 2024. Databases are maintaining the #1 position as the most commonly deployed workload across all 3 years. It shows Kubernetes as a reliable platform for running critical data workloads. Analytics moves up to the #2 position in 2024. Streaming messaging is now at #3 position. The report also shows many organizations see Kubernetes as a foundation for their AI machine learning infrastructure. We collaborated with the Data on Kubernetes community on a white paper to describe the patterns of running data on Kubernetes. The paper was complete and published. We described the attributes of a storage system and how they affect running data on Kubernetes. We compared the running data inside versus outside of Kubernetes. What are the common patterns and features being used? The paper is focusing on databases, but many of the things we discuss in the paper apply to other type of workloads as well. Storage system has attributes as described in the Storage Landscape white paper. For cloud-native database, the type of backend store used, the number of replicas, and so on, all have an impact on the attributes such as availability and durability. We added 2 new attributes here, observability and elasticity. In a cloud-native environment, you have microservices running in distributed fashion. When a failure occurs, it is hard to detect and figure out which component is causing the problem. So it is even more important to have observability system so that you can detect the problem early and stop the failure from happening. Elasticity means that you can scale up and down quickly. It is an on-demand infrastructure so that you can release resources that you no longer need. It also refers to storage tiering, where you can move your data across different storage tiers depending on how often you need to access the data. Regarding disaster recovery, Raffaele will cover that later. We have options to run data inside versus outside of Kubernetes. Deploying and operating databases manually without proper automation is not recommended. So that means we have mainly 2 options. You can use managed database services that are provided by most cloud providers. You can also run data inside Kubernetes. Running data inside Kubernetes is usually facilitated by an operator. The operator uses Kubernetes self-declarative APIs. It reconciles the actual state against the desired state. With the help of an operator, you can automate day 2 operations, such as backup and restore, migration, upgrade, and so on. With operator, you can also leverage third-party tools, such as Prometheus and Grafana for monitoring, Cert Manager for certificate management, and so on. Here's an example of a Kubernetes operator that deploys and manages a database cluster. The database cluster is usually defined by a customer resource, as shown here. So in the CR, the user describes what type of a cluster, he or she wants. The operator reconciles the actual state of the cluster against the desired state defined in the CR spec. This database cluster is using a workload API stiffer set. It has 3 replicas. Each replica has a pod that uses the persistent volume. The persistent volume is provisioned by the CSI driver. CSI defines a set of common interfaces so that a storage vendor can read the driver and have the storage being consumed by containers running in Kubernetes and other container orchestration systems. According to the DOK survey, an organization typically uses more than one operator. In the operator hub, there are more than 300 operators. There are more than 50 database operators, including etcd and Vitas. Those are the 2 graduated CNCF projects. There are also 10 PostgreSQL operators, including Cloud Native PG, that is a sandbox CNCF project. Although operators are widely used while running data on Kubernetes, there are a lot of challenges, including lack of standard. So the DOK community is working on an operator feature matrix, trying to come up with standardized and vendor-neutral feature metrics so that it will be easier for a user to choose an operator. When running data on Kubernetes, there are many common patterns and features being used. We already talked about the operator and CSI. We also mentioned the workload API stiffer set. Topology-aware scheduling is another commonly used feature. You can apply node labels where the key is the topology key. The scheduler can use that information to spread the pods across different failure domains. So that with the topology-aware dynamic provisioning, your persistent volumes can also be scheduled to the failure domain where your pods are scheduled to. The pod disruption budget is another feature that is commonly used. It's a way for the workload to tell the control plane how many number of instances are needed for the workload to work properly when they're doing a planned maintenance. In Kubernetes, there is the default secure networking model. By default, the pods are not accessible externally. You will have to explicitly enable external access. So that makes sure your applications are protected against unauthorized access. Observability is very important when running data in Kubernetes, as I mentioned earlier. There are tools for logging, metrics, and tracing that can help developers monitor and troubleshoot problems. There are also many tools to help you run data in Kubernetes in a secure way. After publishing the DOK paper on database patterns, we started to work on another paper that is focusing on running data analytics and AI machine workloads in Kubernetes. This paper is still work in progress. Now let me hand it over to Alex, who will talk about the performance whitepaper.
Okay. I'm going to touch on this very, very briefly because performance is the sort of thing we could talk for hours on. We've put a performance benchmarking white paper here to explain some of the do's and don'ts and how to do apples for apples comparisons between different cloud-native storage systems. And we were looking specifically at databases and at volumes. As we were going through this, the one constant was that there are definitely more pitfalls and more ways of doing this, getting this wrong. And what you need to focus on is whether you're trying, understanding which area of the storage system and the specific layer in the storage system you're actually testing. So, for example, the client requirements or the performance requirements to handle a large number of operations might look very different from doing a throughput-based benchmark. And of course, all the different layers and the topology and the services that you're using, like data protection and reduction and encryption, affect the overall performance. But often latency is going to be the killer that affects every layer, because that kind of grows with every layer in the stack. And one thing I will emphasize more than most is caching, because in cloud-native storage systems, caching often happens at multiple layers in the stack. And I've lost track of the number of times when you see published benchmarks that kind of highlight performance that is way beyond what the storage can even theoretically provide, and that's because you're effectively benchmarking the cache as opposed to the storage system. So always be critical. Always never believe all of the results, and really understand it. Really understand the basis of the benchmark, and of course, the most important takeaway is vendor-provided results are often not useful for making comparisons. It's really hard to compare those published results to your system. And so it's always important to run your own tests on your own environment with your own applications, because ultimately that's the only thing that matters. Have a look at the link. There's a lot of useful information there and a lot of do's and don'ts, which will hopefully help with the environment. And with that, I'll pass on to Raffaele.
Okay, so disaster recovery, one of my favorite topics. We just recently published version 2 of the white paper on disaster recovery. The main change in this version is that we identified the main archetypes for doing disaster recovery, which are those displayed here in the slide, and we gave equal and balanced space in the document to all of this. In the previous version, we were overweighting the one on the right, which is still our favorite. Everything else being equal, you should do that one because it's more cloud native. So just going over this, and this was timely because with new workloads types coming on Kubernetes, like virtual machines, we are having now a lot of disaster recovery conversation, and these workloads really can only use the two on the left. So the virtual machine, if you want to do a disaster recovery strategy, you can do backup and restores or volume replications. You cannot really use the other ones. So going from left to right, in the white paper we discussed backup and restore. There's no need to explain it. We discussed the various approaches to volume replication. Notice that these two types rely on storage capabilities, right? And then as you move to the right, you have transaction replication. So this is the workload doing the work of replicating the data, right? It's still an active-passive approach. And then finally we get to active-active with, again, the workload doing the work of replicating the data. The storage doesn't have to do anything in this case. And with active-active, you can essentially distribute your workload across multiple data centers, multiple failure domains that can be geographically distributed. And if you lose one of the failure domains, so if you lose one of the data center, the workload still keeps working. You don't have to do anything in terms of disaster recovery process. The event is more similar to an active NHA situation. Oops, next slide. Alex, what do you?
No.
Okay. In the white paper, we go a little bit deeper in the comparison. You can see here that we talk about RTO, RPO, who owns the process. It's worth again highlighting that the first two are based on storage capabilities, and the disaster recovery ends up being owned by the disaster recovery process ends up being owned by the infrastructure team. while the two on the right are more reliant on networking capabilities, okay? And because you need this east-west connectivity to make sure that your workloads can talk to other instances. And because they rely on the workload, so on the middleware, you need, they're typically owned more often by the developer team, okay? So the disaster recovery becomes, it's owned by the developer team. So if you're building a platform where you want to make one or more of these approaches available to your developers for disaster recovery, then the question to ask, that you should ask yourself is, which capabilities do I need to add to my platform to enable these approaches, right? And because Kubernetes, or in general, compute platforms don't come with all of the capabilities that we need. So there are, I collected here the capabilities that we need. So we have backup and restore, volume replication. Global load balancing is always needed because you need to switch the traffic, right? You need east-west communication, and then you need middleware that can do primary, secondary, or that can do fully distributed active-active middleware. I have here examples of CNCF and non-CNCF projects that can enable those capabilities. This slide is incomplete. There are always new options. But the point is, you can upgrade your Kubernetes cluster to provide these capabilities. And then in the white paper, we go a little bit in depth on the fourth one, the one that was on the right, the active-active, to analyze how it is possible, right? Because it's a little bit new or newer. And we look at the concept of replica and partitions and the CAP theorem, it is at the foundation of why it's possible to have active-active, strictly consistent workloads. We look at some of the software that is out there that can do this kind of, that you can use for this kind of deployments. There is much more now. We should probably update the white paper with a new analysis, but you see that each software here, each product has an approach for the replica synchronization or consensus protocol, and for the sharding consensus protocol. So when you have both of them, you can actually distribute and scale your workloads. And then we have a simple reference architecture on how you would deploy these kind of workloads if you have a Kubernetes compute platform. So you need, in this case, for example, you need a way to synchronize the workload with an east-west communication path between the clusters. And you know that Kubernetes clusters have an internal SDN, right, software-defined network, so they're not necessarily routable. We need a capability there to make that work, and then you can have a global load balancer in front of the clusters. You can find more in the white paper, so feel free to download it. We just released version number 2. Back to Alex.
Great. So I will just end this with a community call out. We would really love to have more of you join and consider a role in one of the tags, or to work on some of the initiatives that either help the CNCF projects or with the CNCF projects. And we're looking for more contributors to continue and help build out our community. So look out for announcements on the TRC channel in the CNCF Slack or the TRC mailing list. And of course, myself and the other members of the TRC are available to have a chat and answer any questions you have. And with that, I will open the floor to questions, or are we tight on time? We have a couple of minutes of time, so any questions? Don't be shy.
Thank you. I ask one simple basic question. You started off, and because we had a lot of conversation in my project, you said that there is nothing called a stateless application. Mm-hmm. Is that a matter of figure of fact or just how you see it?
No, so look, every application in some sense is going to store state somewhere, whether it's a database or even just a simple file. And I think whatever the situation is, you can choose to have your storage systems be external to your compute environment and to your Kubernetes cluster, or you can choose to have those internal to your Kubernetes environment and your Kubernetes structure, right? So whether you're storing a simple file on a file system, you can have that file system within your cluster or external. Same goes for databases, object stores, and everything else. And there are pros and cons for both. And obviously, we're here talking about the cloud-native aspects of storage. All right. I think we're done. Thanks, everyone, for coming, and look forward to seeing you soon.